In this section, we're going to look at what happens when we make the input to a system a simple function like a step or impulse input. Now, the impulse input in particular is of great interest because when we have a linear time invariant system, this response to the impulse, which we call H, is going to be useful later in this chapter and throughout signals when we want to calculate the overall response of a system. We're going to see that knowing just the impulse response, as we said in the last lecture, is going to let us know everything we need to know about the system. The impulse response is also related to the unit step response, which takes a look at the same system and asks what is the response to that. So we could think of the unit step that is well approximated by making a input to the circuit a DC voltage that comes on suddenly at time 0. Now, it's not quite a realistic signal because any real-world signal is going to take some at least very short amount of time to raise its voltage up. And the delta, that one can be thought of as the energy concentrated in a very small amount of time. So we're going to take a look at the same circuit your book did, but we're going to look at the problem from a couple different angles that are different from the book. So I encourage you to also look through how they solve the example. So what the procedure we're going to use would work for any linear time invariant system. We're going to show it in particular for a first order circuit. So here we have a input signal. It's going to be an input voltage that can be an arbitrary input signal. In a lot of cases for what we're looking at today, the input X will be the impulse or the unit step, but it could be in general anything that you want it to be. So that input then just goes through a resistor and a capacitor. And this resistor has value R, this capacitor has value C. We label the current as a function of time, so that's related to the driving function X. And then we're going to take our output. We could take our output to be any voltage or current in this circuit, but we're going to do what we typically do, and we're going to take the capacitor voltage to be the output. So now we have a system, which is the electrical circuit. We have X, which is a signal which represents the voltage input, and the circuit then transforms that into another signal, which is going to be the voltage signal Y. So we can write the voltage equation for the circuit. If we look at the current, it's going to be the capacitance C dV dt, right? So it's going to be the capacitance times the derivative of voltage. So that is our current flowing through the circuit at any particular time, because the current through the capacitor has to be the current through this entire circuit. And if we multiply that current, which is going through this loop, by R, now we have the voltage drop across the resistor. And if we add the voltage drop across the resistor to the voltage drop across the capacitor, we have the driving voltage X. So there is the differential equation that describes what's happening in this circuit. Now we'll call the time constant just RC here, and we'll rewrite it in this form by dividing out the time constant. Okay, so now we have the differential equation that we want to solve. Now, if we want to find the impulse response, which is defined as how the system responds when the input is an impulse, and then whatever it outputs we're going to call function H, the impulse response, we need to replace this X with the impulse. So, and then when we do that, the output of the circuit is known as H. So let's rewrite the circuit with that in mind. differential equation in terms of h here. And here I'll write the impulse out explicitly in terms of time. I've been dropping that for the other functions. We'll solve this circuit like your book does using an integrating factor. So the integrating factor for this differential equation is E times t over tau c, the time constant. So we just multiply the whole equation through by that integrating factor. And then let's take a look at what's happening on the right-hand side of the equation. On the right-hand side of the equation, we have a delta times some time-varying function. Now we know from the sampling theorem that we can make use of the fact that the delta is 0 almost everywhere. So this expression e to the t over tau c isn't having a time varying effect. All that matters is what's happening when small t is equal to 0, because when small t is not equal to 0, the delta just zeroes that out. So what we can do to simplify this is we can say the only value that matters in the expression that's multiplying the delta is when t equals 0. So we can simplify this whole expression here by substituting in t equals 0. So the exponential drops out, just becomes times 1, and we're actually left on the right-hand side with this. So then what we do on the left-hand side is we recognize that this is what comes out of the product rule when you take the derivative of the function h times e to the t slash tau c. So think of, when you see h here, think of h of t. We're just using a simplified notation and not writing that dependence when it's obvious. So now we can see that this step is reversible. If I take the derivative and use the product rule, I do get what's on the line above there. So now the next step is we're going to take the integral of this, and we're going to take the integral from the left side of 0, and it's important when we're dealing with the delta that we think about whether we're starting immediately left of 0 or immediately right of 0, because if you pass over 0, you pick up the area of the delta, but if you don't actually pass over 0, we'll actually miss the area of the delta, and it will be 0 everywhere. So what we're doing on the left-hand side is we're integrating a derivative. So those are reverse operations. So what we end up with is the function h, and I'm going to write it here in terms of a substitute variable, tau, and then we have e to the t, but I'm using the substitute variable tau, and then the constant tau c. And we are integrating from the left side of 0 to t, so we substitute in the values here for our substitute variable tau from 0 minus up to t. And on the right-hand side, we also do the same integration from the left side of 0 up to whatever t is, and we realize we're just integrating over a delta function. So here we still have the constant out front, 1 over tau c. When you integrate over a delta function, you get the unit step, as we know from last week. So now we expand the left-hand side, and we substitute in the variable tau here. On the upper limit, tau becomes t, and on the lower limit, tau becomes 0. So we're going to go ahead and substitute that in. So we're going to have h of t, that's the function we're ultimately trying to solve for, e of t divided by tau c minus h of 0 minus e to 0 over tau c, so e to the 0. And on the right-hand side, we still have the same thing. So on the left-hand side, this term right here goes to 0. That is saying, what is the response that the system outputs on the left-hand side of 0? And the input has not come yet. This is immediately before the delta comes, so the response out of that, we know the initial condition is going to be 0. So on the left-hand side, all we have left is the function h that we're trying to solve for times this term, and we are going to divide out that term from what's on the right-hand side to get our answer. So our answer is h of t, 1 over tau c, and I divide out, so I get e to the negative t over tau c, and it's times u of t, because the impulse response starts at 0. So we get the exponentially decaying voltage, which is what we expect. So what this says is you have a voltage source. It's an impulse. It is very high for a very short amount of time. So maybe it's 100 volts for 1/100th of a second. So it has area 1, an area of 1 volt seconds. And this impulse is the limit. As that impulse gets shorter and shorter, but then the voltage has to go higher and higher to give us this, the input of 1 volt second, which is the area under the delta. So this derivation is similar to the one in your book, but I do also want to show you that we can get the same result using the Laplace transform. So what we're going to do on the next slide, we're going to take this equation right here, and we are going to solve it using the Laplace transform. So our differential equation is RC y dot plus y equals x, same as before. Now we apply the Laplace transform, so RC s y, so that's y of s, right? I'm just not showing the dependence on s. We understand the capital letter y and x represent Laplace transforms. And on the right-hand side, I have capital X, the Laplace transform of the function x. Now, what we need to do to get the impulse response is we need to figure out, if I want to make x of t equal to the impulse, then what is the Laplace transform of that? So let's look at the definition of Laplace transform. And into this, we need to substitute in the delta function, which is our input. And this is going to be understood there to be 0 minus. And now, as we evaluate this Laplace transform, we apply the sampling theorem. And the sampling theorem says when you integrate over the delta, since that delta zeroes out the integrand almost everywhere, the only place we care about it is when t equals 0. And when t equals 0, we substitute in for the rest of the expression, so we have e to the minus st. So e to the minus s times 0. So we have e to the 0, which is times 1. So it's just integrating times 1, and we get the area under that, and the Laplace transform of the delta is very simply the value 1. So there's no s, the s disappears. There's no, you can think of x as the complex frequency variable. There is no frequency. This is just a impulse that has no frequency dependence. So it's independent of s, it has all the frequency components. So x of s here is equal to 1. So then we can substitute in Laplace transform of the input is 1, and now our output we call h, so I'll substitute in capital H. So I solve this for h by factoring. So that was just rearranging the equation. Now I'm going to go ahead and substitute in. We called RC the tau c, which is the time constant. And I can rearrange this here into a little more familiar form where I am going to factor out a tau c of both the numerator and the denominator. So if I factor out tau c from the denominator, I have s plus 1 over tau c, and in the numerator I have to also factor out 1 over tau c. The reason I did this is because you can find an expression like this in Laplace transform tables, as you know from differential equations. So I have a denominator of s plus a constant, and I can do the inverse Laplace transform of that. We have the numerator is just a constant scaling, so that comes out front here. And then I do the inverse Laplace transform. And if I look that up in a table or work it out, we'll see that it is this exponential decay. And it starts at time 0 for the Laplace transform. This is the same result we got on the previous slide. So what we're showing, as you already knew from differential equations, is the Laplace transform is a shortcut method for solving differential equations. For our next step, what we're going to do is we are now going to use the original method to find the step response. Now remember, we had this differential equation before. We had derivative of the impulse response was equal to 1 over the time constant times the integrating factor times the input, which was the delta. And then we went and we simplified that equation in a certain direction by using the fact that the delta was 0 almost everywhere. But now what we're going to do is we're going to make a couple changes to get toward the step response. We're going to make the input here, I'm going to replace it with the unit step. Then what we have is the output would not be called h, but we would call it s, s of t, the unit step response, and the rest of this is the same. And now we have to solve this differential equation. So again, we are going to apply integration from the left side of 0 up to the current time. And when we do that on the left-hand side, we get s of t times e to the t divided by tau c. So that's the upper limit. And then I get subtract the lower limit. So I'm doing the integral of a derivative on the left-hand side. So I'm just evaluating that expression in parenthesis above. So the lower limit, I get s at 0 minus times e to the 0 divided by tau c. So that's the left-hand side. Now, step response is going to go to 0 on the left-hand side because this is the input has not occurred yet. And on the right-hand side of this equation, when the value of t is greater than or equal to 0, I am going to have this value. I'm going to have 1 over tau c integrating from 0 up to t of that integrand, e to the, let's call the variable tau here. And it's the unit step value is going to be 1 in that range. So I'm just multiplying times 1. And I integrate over the substitute variable tau. Now, I said when I started this that that's what happens when t is greater than or equal to 0. Then we're in the range where that unit step is on, and this is the expression I get. If t is less than 0, then that quantity I'm integrating is from 0 to a negative value t, so I'm only seeing the part of the function where the integrand is 0, because I look at negative values of t and there's a unit step of t in there. So I multiply this result by u of t to accomplish that. So now when t is negative, I am zeroing out that left-hand side. When I integrate the right-hand side, I am going to have to multiply by tau c, so that 1 over tau c term disappears. And what I'm left with is e to the tau over tau c, and the limits of integration here are tau goes from 0 up to t, and again this expression applies for only for a positive t. If t is negative, we have 0. Left-hand side of the equation, I still have s of t times e to the t over tau c, and now I can simplify the right-hand side by substituting in, first of all, tau equals t, and then tau equals 0, so I get e to the 0. And now I'll divide out by that integrating factor. And I have the step response is an exponential decay toward 1, that is 0 for negative t, and it has a time constant equal to tau c. For our final example, we're going to tie it all together. We are going to let the input function be a rectangular pulse, and the rectangular pulse is going to start at 0, and it is going to end at time capital T. And what I'm going to do is I'm going to force the area to be 1. So although this is capital T seconds long, I am dividing the voltage to be 1 over T so that the area under this input voltage is 1 volt second. So this is a rectangular pulse starting at 0 and going for T seconds with height 1 over T. So that is our input. Now we know that the circuit is linear, and we know that therefore it obeys superposition. So the output, let's first of all remind ourselves what the output is for a step function, because the input is really just the sum or the difference between two step functions. And on the previous slide, we showed that the output of the function for a step, the step response, is equal to this. It is equal to 1 minus e minus t over tau c, but only it's only non-zero for positive values of t. So that's the step response. This green function is the sum of two steps. So we can apply superposition to say the output is going to be the linear combination of the outputs that you would get for each of these inputs individually. First thing is the input is scaled by 1 over t. Linear systems have the scaling property, so the output will also be scaled by 1 over t. That's a constant. Then we will have the output due to the unit step, which is just going to be what we derived on the last slide. It's 1 minus the exponential decay here. That starts at 0, so I have that unit step. And then I have I have to subtract the response to this subtracted input, which is a step in the negative direction occurring at time t. So applying the time shift property, since we know that the system linear circuits are also time invariant, if I delay the input by t seconds, I can replace all the t's in this output with small t minus capital T to delay them. And that's exactly what we'll do here. So this term is going to be 1 minus e to the minus. Now t gets replaced with t minus capital T. Notice I need those parentheses there. I'm replacing the expression t with the expression t minus capital T. And then the rule says take the negative of that argument. And there's the time constant. And that is going to be multiplied by a unit step. Again, I replace t with t minus capital T. And there we have it. So now our goal is to simplify this. And what we're going to do is we're just going to look at it piecewise in 3 pieces. When t is less than 0, both of the unit steps are 0. So the output is 0 when t is less than 0, as we would expect because the input pulse did not turn on until time equals 0. Then let's look at the range where the first unit step is on, so t is greater than 0, but the second unit step has not come on yet. So small t is less than capital T. So this unit step is going to be 0, and this unit step is going to be 1. So in that range, all I have is my output is this value right here, scaled by the 1 over t. So I'll have 1 over t, 1 minus e to the minus time divided by tau c. And this expression is valid when t is between 0 and capital T. Finally, I will have the final part of this where the time is greater than capital T. So I will have both of the expressions in the parentheses, and I will have to subtract them. So the ones will cancel out, but what I will be left with is the second expression, so minus negative, so I'll put that one first because it becomes positive. And then subtract the first one right here. This term is negative, so it's going to come up right here. This is our expression when t is greater than capital T. Now we can rearrange this a bit, which will be useful in a minute. We're going to factor this into a term that varies with time and a constant term, just to see what's going on a little better. So the term that varies with time is the first part, so we factor that out, e to the minus t minus capital T, and we're going to factor that out of the rest of the expression. So we have left 1 minus, and now we subtract exponents, and we end up with e to the minus capital T over tau of c. The small t's disappeared there. They both have a small t. I subtract exponents, and that is what I am left with. Now let's just do a check. Let's evaluate y of t at capital T from the right side. So we use the final expression where t is greater than t, and we substitute in small t equals capital T. So our term out front here is going to be, this is going to be e to the 0, so it's times 1, and then I just have this constant right here in the brackets left over. And we see that expression exactly matches this expression right here when this small t equals capital T. So the expression for this second segment and this expression for the third segment, they agree when small t equals capital T. So the limit from the left and the limit from the right agree. My output voltage does not suddenly change. It starts changing the direction it's moving. It has a discontinuous derivative, but its value does not suddenly change. So there we have an expression. In the attached MATLAB, I will let you graph this for various values of the time constant tau c and capital T, so you can see what this function looks like. But briefly, let's do it briefly. If we have t is somewhat less than, so let's say it's much less than tau c, what you're going to find out is we very rapidly charge up the capacitor, and then we have this exponential decay happening. So that is what happens when the time is a lot less than the time constant. If the time is a lot more, the shape gets a little more complicated, but you can plug in the values or use the MATLAB script or a graphing calculator to see what happens. The final thing we're going to do is we're going to take this response and we're going to take the limit as capital T approaches 0. So we're going to squeeze that green pulse in the upper right hand corner so it's narrower and narrower but higher and higher, so its area is always 1. And we're going to see what effect does that have on the output. Well, this middle term, as T approaches 0, this will happen for an infinitesimally small range, so this middle item will disappear. And as I let T go to 0, what we're going to have is we're going to have division by 0 happening. But if I look at what's happening in this expression, the numerator is also going to 0 as time approaches 0. So if we want to figure out what's happening to this function as capital T approaches 0, we have a form that is 0 over 0, so we go back to calculus and we will apply the L'Hopital's rule to that. So what you're going to do is you are going to say, I want to take the limit of this function as capital T approaches 0. So we look at the two parts again. So this is the segment we're working with. This one is the only one that varies with small t. Now this part outside the brackets, as capital T goes to 0, this is just, oh, and we forgot divide by tau c there. This part, as capital T goes to 0, is just e to the minus t over tau c. So that one is well behaved. But where we need L'Hopital's rule is to deal with this part as capital T goes to 0. As capital T goes to 0, the numerator is 1 minus e to the 0, so 1 minus 1, so numerator is 0, denominator is 0. So what I need to do is I need to take the derivative with respect to capital T as T goes to 0 for both the numerator and the denominator. So when I take the derivative of the numerator with respect to capital T, I just get 0 here minus, and then I'll get 1 over tau c and the e to the minus t. So let's write that down. So 0 minus 1 over tau c e to the minus t over tau c over 1. So that's the derivative with respect to capital T. Now I have a form where I can safely substitute in capital T equals 0. When I substitute in capital T equals 0, all that is left is 1 over tau c. We forgot a negative sign there when I took the derivative. There was negative 1 over tau c. So what's left here is 1 over tau c for that factor. And then if I put that all together, since that was just what happens to the term in brackets, this term in brackets as capital T goes to 0, we've shown that that's the reciprocal of tau c. Then I have left so there's my 1 over tau c, and then I have left this part, which I did not need to apply L'Hopital's to. I just let the capital T go to 0 and it was well behaved, e to the minus t over tau c. And I need to multiply that whole function by the unit step, because when we started this we said that This is the evaluation for small t is greater than capital T, and we let the capital T go to 0. For small t less than 0, this rule still applies. So we zero out the function for t is less than 0 by multiplying by u of t. This result here is the same as, and this is why I called it h, it's the same as the impulse response that we derived at the beginning of the lecture. So we can see that by letting this unit area pulse get infinitely narrow, but high enough so that its area corresponds to 1 in the limit, the output will be the same as what we derived on the first slide. But if it's not infinitely narrow, we have this other form where it has a finite amount of time to ramp up before it starts decaying. What I encourage you to do now is take a look at the MATLAB script. There's comments in there explaining this a bit further, and then you can run and generate these graphs for various values of the time constant tau c and various pulse widths capital T.